And good evening, everyone. Hope that you have good weather where you are. We're so glad to have you with us here tonight for our Mars MAVEN science presentation. Tom, please introduce tonight's speaker.
Okay, thanks, Christine. Can you hear me?
Yep.
Okay, my name's Tom Mason. I am the Communications and Outreach Coordinator for the Laboratory for Atmospheric and Space Physics at the University of Colorado. And I'd like to introduce you to tonight's MAVEN webinar presenter. Dr. Frank Eparvier is a senior research scientist at LASP, which is the Laboratory for Atmospheric and Space Physics. Frank received his degree in physics and mathematics from the University of Wisconsin and his PhD in astrophysical, planetary, and atmospheric sciences from the University of Colorado. Frank is the principal investigator on the extreme ultraviolet and X-ray irradiance sensors on the NOAA GOES-R satellite series. He's the instrument and project scientist for SDO-EVE, the instrument lead on the MAVEN EUV monitor, and the instrument scientist for the timed C experiment. Frank's research interests are in the areas of solar irradiance variability and its effects on the upper atmospheres of the Earth and other planets. Frank has been active in LASP and MAVEN EPO activities over the years, and we really appreciate his willingness to participate in many of our projects. I look forward to hearing his presentation this evening. Frank, if you want to start sharing your screen.
Okay.
If you're able to, take it away.
Welcome everyone. I have to find my presentation. Make sure it's shared. All right. And I'm going to stop my video so I can pick my nose and rub my eyes and do things I don't want you to see.
Perfect.
All right, so I'm going to talk about the sun's influence on planetary atmospheres, and feel free to interrupt me anytime with questions. You can type them in the chat, but I can't guarantee I'll see them until later since I'll be doing my slides.
What we'll do, if it's all right with you, Frank, every now and then, when you pause, we'll let you know if a question has come up in between pauses.
Okay. So I'm assuming everybody can see my slides okay. It says, who am I? Tom has already given me an introduction, but I'm a senior research scientist here at LASP, and my background is in the field of aeronomy, which is the study of how energy inputs drive the physics and chemistry of an upper atmosphere, in particular the Earth in most of my studies, but also Mars and other planets. I'm an experimentalist or an instrumentalist. I like to measure things. I like to build instruments to answer interesting questions through measurements. And I strongly believe that experiment is the test of all knowledge. I currently work on a bunch of projects, as Tom already said, so I don't need to go into those. Tonight I'm going to tell you a bunch of stories. First, a personal recollection, and then talk about a historical event having to do with space weather, and then talk about the here and now, how space weather interacts with the Earth, and then I'm going to talk a little bit about there and now and then how space weather affects other planets, and in particular Mars, since this is a MAVEN webinar and I have an instrument on MAVEN. So my personal story starts when I was the summer between my freshman and sophomore year in college at the University of Wisconsin. I had a job at a candle factory in Oshkosh, Wisconsin, and I lived in Neenah. And that job had me working late at night. And one night I was driving home about 1 o'clock in the morning along the shores of Lake Winnebago. And I looked out the window of my car and saw lights in the sky. And being a budding astrophysicist, astronomer, I pulled over. I had a chase lounge in the back of my car and a pair of binoculars, and I sat in a farmer's field and stared up at the sky and saw the northern lights. In fact, in 1983, that August, there was a very large auroral substorm, and the northern lights were seen all the way down into Illinois, but they were basically filling the sky in my hometown of Neenah. And seeing something quite a bit like this, and was fascinated by it. I was a physics and math major at the time, and I wanted to understand what was going on, and that was pretty much the start of my journey into becoming a space weather scientist. Now I'll go into a story that probably many of you have already heard. Way back more than 100 years ago, 150 some years ago, in September of 1859, a British astronomer named Carrington was sitting in his observatory and looking at the sun, of course not with his eye through the telescope, but projecting it onto the wall, and he witnessed a white light flare, so a flare on the sun. Most of the time today we observe flares in other wavelengths, but when it's a white light flare, that means it's a really bright flare. And he watched it and drew pictures of it. They didn't have good video cameras or anything back then. And he watched it last for a few minutes. And then here's a video of what a flare like he looked at and drew looks like today. This is from the SOHO mission in the year of 2000. July 14th, we call this the Bastille Day flare, and it's one of the more studied flares. But back in 1859, on the very next day after Carrington saw this flare, all heck broke loose on Earth. Telegraph operators around Europe and the United States had all sorts of problems. They could transmit without turning on their power. They were having overcurrents going on all their wires, and sparks were flying from equipment, and even some telegraph stations burned down because of that extra surge of energy going through their wires. And the aurora, like I saw in Wisconsin in the 1980s, were also seen all the way down to the Caribbean, to Hawaii, Rome, Hong Kong, so way down south into almost tropic. Usually the aurora are confined to the northern regions. And at the time in 1859, people speculated what they were, but they didn't really understand. And Carrington published a speculation that the flare he saw in the sun and the aurora and things happening in telegraph stations around the world were connected. And a lot of scientists, because it was a new idea, poo-pooed it. He got a lot of criticism. And the whole idea that the sun and the earth were somehow connected was a radical idea at the time. Today, we understand that the sun and the earth are a complex and connected system, and we call that system space weather. And I'll expand that to not just the earth, but the entire heliosphere, or the influence of the sun that goes out to the edges of the solar system and includes all the planets. Here's a diagram that very simply explains space weather. There will be a quiz at the end, so I hope you're paying attention. This basically is just showing all the different things happening on the sun and how they can interact with the Earth and the Earth's magnetic field and the Earth's upper atmosphere. And over the years since Carrington, we've studied all these different links and reactions and sources through making measurements from the ground, making measurements from space, and applying various theories and computer models and mathematical models. And now we actually have a whole system understanding of what's going on, and we try to monitor all the different pieces so that we can model what the future impacts and present impacts of space weather will be. So the story of space weather starts, of course, with the sun. The sun gives off energy in all sorts of ways. It gives off a lot of light. It's when you look up in the sky, it's the brightest thing we can see. It's giving off light at all different wavelengths. So we tend to see in the visible but a lot of energy is coming in the infrared and the ultraviolet and all the way down to X-rays. And depending on the wavelength of light, how it interacts with the planets varies. And the sun is also giving off what we call the solar wind. It's a stream of charged particles and magnetic fields that are coming out from the sun, sometimes smoothly, sometimes in clumps. And the sun is constantly changing on all time scales, from seconds to centuries and everything in between. It also changes on all size scales, from millimeters to megameters. Megameter is 1,000,000 meters, or 1,000 kilometers. Here's a movie of the sun, surface of the sun, the photosphere, in the visible. And each one of these, we call it a granule, is a convection cell. The sun is a big ball of hydrogen, and near the surface, it's moving and being heated from below by the nuclear furnace in the center. And that heat from below, of course, causes convection, just like boiling in your a pot of water on your stove. And these convection cells are about a megameter across. So 3 of these would fit in the United States, essentially. So these are very large convection cells. The sun above the surface, if we look in X-rays and ultraviolet light, we see that it has, let me play that movie again, very complex magnetic fields, and material is heated and rises up along these magnetic field lines, and we see that it's constantly changing. If you watch the time here, this loop is about a couple of hours long, and the magnetic fields on the sun are continually evolving and changing. Here's a movie from the Solar Dynamics Observatory showing the sun rotating. This movie lasts a day or two, and you're looking at the knots of magnetic field and material moving along and being heated and getting brighter in the X-rays and ultraviolet light and evolving, and you see flares going off that happen in minutes, but have an impact that takes over the whole sun in terms of brightness at particular wavelengths. Here's a image of the solar wind, of material streaming out from those magnetic openings in the solar atmosphere, and this is basically just plasma, heated and ionized particles, electrons and protons, being spewed out at hundreds of kilometers per second, and heading out and interacting with the planets. So this is showing about a week to or so of activity, and each of these knots or blobs coming off is what we call a coronal mass ejection. We saw those loops in an earlier movie of material along magnetic field lines. Sometimes when a flare goes off, those loops pinch off and they spew out, and a bubble of plasma or hot solar atmosphere gets spewed out into the solar system. The sun goes through activity cycles on all different timescales. The most common that you've probably heard about is the 11-year solar sunspot cycle, and that's actually a half of a 22-year magnetic cycle, where the sun starts with a normal dipole magnetic field like a bar magnet, but then it gets all twisted up and knotty, and then you get sunspots and active regions and all of that weird activity that forms, and CME is spewing off from the sun, and the sunspots and the brightness of the sun actually increases on a 11-year cycle, roughly. Some solar cycles are 10 years long, some are 15, but on average it's about 11. Now, what does all this variability on the sun do to the planets? Well, if we look at photons, the light coming from the sun, in particular in the ultraviolet and X-rays, On Earth, let's start talking about just Earth in the first place, because we're here on Earth, we know the most about it, we can study it the most easily, and then we'll talk about other planets later. But ultraviolet light and X-rays from the sun are all absorbed in the upper atmosphere. Only the visible makes it down to the surface. And when photons are absorbed in the atmosphere, it can do one of three things. It can heat the upper atmosphere, and you'll find that temperatures up, say, 200 kilometers above the surface can range from 500 to 1500 Kelvin. It's that part of the atmosphere is called the thermosphere because it's hot, because it's absorbing all of these ultraviolet and X-ray photons from the sun. And the variability from 500 to 1500 Kelvin is from solar minimum when there's very little solar activity to solar maximum when there's a lot. So variability of the output of the sun changes the temperature of the atmosphere by a factor of 3. When you heat something, it expands. So when the atmosphere expands, oddly enough, you think about when it expands, it should get less dense. But if you're at a particular altitude and you expand the atmosphere, the density at that altitude will actually go up. And that becomes a problem for satellites that are orbiting low in low Earth orbits, say 400 or 500 kilometers, like the space station and such. They experience more drag when there's more solar activity. If any of you are old enough to remember Skylab, Skylab came down earlier than expected because we had a very active solar cycle and the atmosphere expanded and increased the drag on it. Another thing that light from the sun can do when absorbed in the upper atmosphere is ionize it. Ionization is when an electron is knocked off of an atom or a molecule, and you have free electrons floating around, and then you have positive ions floating around. And we have a layer of the Earth's atmosphere called the ionosphere just because of these energetic photons or short wavelength light from the sun. And if that output from the sun changes on timescales of flares, which is a few minutes to hours, or timescales of days, solar rotation, you saw those active regions as they rotate around the sun. It's kind of like a lighthouse, and a beam of bright light goes by, and the atmosphere of the sun or of the Earth can get ionized more or less depending on how that rotates around. You also get large day-night changes on Earth because you have sunlight in the day and you don't at night. Finally, sunlight in the ultraviolet and X-rays can break apart molecules, dissociate them, and that changes the chemistry and the constituency of the upper atmosphere. Down here at the surface of the Earth, the atmosphere is about 78% nitrogen molecules and 20–21% oxygen molecules. But up above, say, 200 kilometers, the dominant species of the atmosphere is atomic oxygen. And that's because things have broken apart and the chemistry has changed it. And you get other odd molecules from photochemistry, like ozone, which is 3 oxygens stuck together. If you have a free atomic oxygen floating around, it can react with molecular oxygen, make ozone. So here's
we have a quick question on that topic.
Sure.
Can the sunlight cause synthesis of new molecules?
So the answer is yes. I just told you about one, which is ozone. Another one that we see a lot in the upper atmosphere is nitric oxide, NO, which is actually not stable down at the surface, but is more stable in the upper atmosphere and constantly being created by breaking apart N2 and O2 and then recombining and making NO. And so you get a lot of layers of different chemicals in the upper atmosphere, and I've got a plot later on that shows some of that. So here's a plot of the spectrum of the sun in blue. So this is wavelength from X-rays and the EUV to the visible out to the IR. And the visible is where the sun is the brightest. and it looks like a nice smooth black body curve. But when you get to the short wavelengths, the output of the sun is very different. It's atomic emission lines and continua, and so you get very spiky and non-smooth spectra. And the red line shows the amount of variability over the 11-year solar cycle, and you see that in the visible, it barely varies at all. It's 0.001, a 0.1% variability in the visible over a solar cycle. Yet down here in the short wavelengths, you can get variability on the order of 100 or 1,000%, depending on what's going on. Like when a flare goes off, some of these wavelengths will increase all the way up to here where my arrow is. Now, how does this impact the Earth? If you think about our atmosphere, it's made up of, in the beginning, nitrogen and oxygen, but once you expose it to light, that kind of changes. This is a plot showing altitude above the surface in kilometers and wavelength of sunlight, and this line is showing the depth at which the sunlight is absorbed in the atmosphere, or where it deposits its energy. And you see that the extreme ultraviolet is absorbed very high up, and that creates and heats the upper atmosphere, makes the thermosphere. It also ionizes the atmosphere in this range from, say, 60 kilometers on up to the top. And then you get less and more depth of penetration of the longer wavelengths. So here is the ultraviolet, the far ultraviolet, middle ultraviolet, and near ultraviolet. And then once you get up to the visible, around 400 nanometers, it all makes it to the surface. And you can see that there are various things absorbing at various heights. And so you get different chemistry going on at those different altitudes, and you get different temperature effects at those different altitudes. Here's a plot. We don't have to talk about it too much, but it's showing the density of different species of the atmosphere, and you see nitrogen down at the surface is this is a log plot, the most dense species, and then oxygen, O2, is the next dense, and they stay hand in hand, well mixed up until you get to about 100 kilometers, and then they start to separate, and that's because of gravity and low density. They're no longer colliding with each other and becoming well mixed. They're acting independently of each other, and you also start to get things like ozone being formed. You get the ozone layer down here at the middle atmosphere, and you get this atomic oxygen being created about 100 kilometers, but also higher up it becomes the dominant species. And if you go even higher than that, like say 500 kilometers, then the atmosphere is entirely hydrogen, and all these other things are just minor species. The temperature of the atmosphere down here at Earth, where it's all well mixed, the temperature goes down as you go up in altitude. I live here in Boulder. Actually, I work here in Boulder, but I live 3,000 feet up in the mountains, and the temperature is usually about 10 degrees colder at my house than it is in Boulder, because I'm about 3,000 feet higher. The temperature is dropping, and that's just due to mixing and expansion. And but then you get the temperature turns around and starts to increase, and this increase is because of absorption of ultraviolet light heating the atmosphere, in particular ozone, that ozone layer we saw that's created by the ultraviolet light, and it absorbs ultraviolet light and heats the atmosphere up. And we have what we call the stratosphere, where the temperature turns around and increases. Then you go even higher and it decreases, and it's decreasing because the air is thin and it's radiating energy out into space. But then you get up to about 80 kilometers and it turns around, and you get this great heating going on by the soft X-rays and ultraviolet, extreme ultraviolet light, and that's the thermosphere. So the temperature up there is really, really hot compared to down here at the surface. Now, if you look at this, well, I've shown the range of variability in these dashed lines for over the solar cycle, but that also can vary from day to day because of solar activity. The ionosphere is basically above, say, 50 or 60 kilometers. The ultraviolet light is penetrating and knocking electrons off of atmospheric species, mostly nitrogen and oxygen, and creating the ionosphere. And this is the amount of free electrons being created, or the density of the free electrons. And you can see that day and night you have drastically different. You turn the light off and ionization goes away, and it goes away dramatically by 3 orders of magnitude. And that's why when you're driving around at night in the summer, you can sometimes hear radio stations all the way from several states away, because radio waves bounce off the bottom of the ionosphere. And if the ionosphere is high up at night, that means the radio waves bounce off much higher up, and they can travel much further around the curve of the Earth. Solar activity with solar minimum to solar maximum can change these profiles quite dramatically, and it's when a flare occurs, it can be even greater than solar maximum. We get penetration down to even deeper layers, and these different bumps in the ionosphere are due to different species absorbing the photons, and sometimes these will pop out and be very large extensions during a flare and cause disruptions to communications and such. And the Earth's ionosphere is basically a big dynamo, electrodynamic system, and there are currents in the upper atmosphere. Winds move the things around. You have a source of electricity on the daylight side and a sink on the dark side of the Earth, and you get currents traveling around the planet, and you get them traveling north to south in the polar zones to the equator. And so with solar activity, these currents are disrupted, and you get very different changes in the ionosphere. And people like at NOAA, at the Space Weather Prediction Center, will observe the sun and watch a flare go off, and they'll predict how the ionization and these currents is going to change, and how that impacts communications, how it can induce currents in wires like the telegraph wires in the 1850s. We have wires all over the planet now, power grid wires, telephone wires, pipelines, cables under the ocean. All of those can pick up these induced currents that are going on in the upper atmosphere, and you can have surges of electricity on wires on the ground, and that can blow out transformers and cause blackouts and things like that. At the longer wavelengths, most of the energy from the sun is in the visible, and it's reaching the surface of the Earth. And we study the radiation budget of the Earth, how much energy reaches the surface. It heats the surface. Some is re-radiated to space. Some bounces off clouds. Some is absorbed by clouds, absorbed by water, and you get this very complex budget of energy. And this is what climate people study, and they measure how much is coming in from the sun, how much is going out into space, and what these different processes are doing to the budget and to the climate. Now, the other thing I talked about that the sun puts out in the solar wind are these energetic particles, electrons and protons, and magnetic and electric fields also. So you have the solar wind streaming out. You saw that movie of that with coronal mass ejections. The IMF is not the International Monetary Fund. It's the Interplanetary Magnetic Field. I was actually surprised as a space scientist to hear that there was a thing called the International Monetary Fund, but because it was always the Interplanetary Magnetic Field to me, but that's what you get for being a nerd. So when the solar wind and all of these disturbances in the solar wind hit the Earth, various things can happen. You can get magnetic fields from the sun interacting with the Earth or other planets' own intrinsic magnetic fields, and compressing it and shaking it up, rattling it, changing the direction of fields depending on how strong the solar magnetic fields are. And that can do a lot of interesting things. And energetic particles being carried out on the solar wind can either penetrate the Earth's magnetic shield, our magnetic field, or be diverted by it and get trapped in the radiation belts or in the tail of our magnetic field behind the planet, which is kind of like the wave behind a boat in an ocean as the magnetic field strips by. And the trapped particles can follow the magnetic field lines of the Earth and hit the Earth's upper atmosphere at high latitudes near the poles, and can ionize and add extra sources of ionization and change the electrodynamics of the Earth's atmosphere, but also make the aurora. So we've come full circle to my high school days or college days. Also, if the magnetic field is disrupted, the particle effects can extend further down in latitude. Instead of being in Alaska and northern Canada and Russia, the auroral zone can extend all the way down to the middle of the United States or even the Caribbean in extreme cases. Here's a model that the government produces. They take data and they observe the sun, and then they model how the solar wind streams out into the solar system. So here we have the sun at the center, the source of everything. These lines show magnetic field lines coming out from the sun, and they're in a spiral because the sun is rotating in the center of that, and the magnetic field lines are traveling outward. And when you have a rotating source, you end up with this big spiral. We call it the Parker spiral, after Eugene Parker, the scientist who figured that out. And here we have a coronal mass ejection coming out, and this model is showing how it's predicting how it's going to travel through the solar system. Each one of these different things is a different planet. So here's the Earth right there. That CME just gives a glancing blow to the Earth. Here's Mars. Venus itself gets hit by that CME quite onward. So the NOAA Space Weather Prediction Center and Goddard Space Weather Program at NASA will run these models and predict. They'll see a CME go off on the sun, and they'll predict where it will go and send out alerts and say it takes about 3 days for that coronal mass ejection to get out to the Earth distance. And if it comes straight at the Earth, then we know something's going to happen at Earth. Here's a animation, some of you may have seen this already, of a coronal mass ejection coming off the sun. So here we are looking at the sun, and a flare goes off, and you get this blob of plasma shoots out into space. There's the flare, and it's shooting out into space, and now it's traveling for 3 days along this Parker spiral. And here's Earth sitting there with its magnetic field and magnetic tail, and the blob of plasma has magnetic fields, and it changes the Earth's magnetic fields and disrupts it and shakes it up and rattles it, and ends up ionizing and causing the aurora at high latitudes. So what about other planets? The space weather we talked about at Earth was dominated by our distance from the sun. So if you change the distance from the sun, the amount of the density of the photons and particles that are coming out and reaching the planet is going to change. You go to Mars, which is at about 1.5 times the distance from the Earth, the photon and particle fluxes will be cut down by 1.5 squared. We call it the 1/r² issue. So as you go out into space, everything is expanding further and further away from the sun and having less and less influence. So by the time you get out to, say, Jupiter and Saturn, the amount of photons and the amount of particles hitting the planets is much, much less. Whereas if you're in at Venus, you're getting much, much more. Also, planets have different magnetic fields, and I've got a diagram to show that. Jupiter has the largest magnetic field, which is much, much larger than the Earth's. And it's a nice big dipole like the Earth has. Venus doesn't have an intrinsic magnetic field. It has an induced one because the sunlight and solar wind are hitting the atmosphere and ionizing it and creating electrodynamics, and that creates a magnetic field, but it's the opposite polarity of what you would expect because it's induced rather than intrinsic. You get out to Uranus and Neptune, and they have very bizarre magnetic fields that have different moments. It's not a nice dipole like a bar magnet. It's more like 4 magnets put together, and how the solar wind interacts with a magnetic field like that is very complex. Different planets have different atmospheres. Earth has this nice nitrogen and oxygen atmosphere, and we can understand the chemistry. But you go out to the outer giant planets, and their atmospheres, like Jupiter and Saturn, are mostly hydrogen. And you have very different chemistry going on there. In fact, at Jupiter and Saturn and Uranus and Neptune, you get some very complex hydrocarbons formed. When you look at pictures of Jupiter, you see all different colors. Those colors are hydrocarbons that have been formed by sunlight, breaking apart hydrogen and carbon dioxide and methane, and recombining them into long, complex molecules. Other planets like Mercury barely have an atmosphere at all. And so the sunlight isn't absorbed. There isn't much of an ionosphere. The sunlight hit all of it, even X-rays, hit the surface of the planet. Venus and Mars are mostly carbon dioxide in their atmospheres. Venus has a huge atmosphere, about 90 times that of Earth, and Mars has an atmosphere that's just a tiny fraction of what Earth's is, although we think Mars once had an atmosphere similar to Earth or Venus. We think Earth had an atmosphere similar to Venus's in the first place, but that changed over time for many different reasons. And we'll talk about some of that, how planets have evolved over the history of the solar system. So here's, to illustrate some of those topics, here's a plot showing distance from the sun versus the temperature on the planet due to mostly due to the distance. You see, as you get further and further away, things get much, much colder. But there are some oddities, like Venus is way above this curve of what it should be because Venus has a very thick carbon dioxide atmosphere, and you get the greenhouse effect where sunlight goes in, but it can't get out, and it just heats up the atmosphere. And Earth has a slight greenhouse effect. We're just above that line. And Mars barely has any greenhouse effect at all. And then the other planets are pretty much along the line of distance from the sun and temperature, mostly because they're so far away that other processes are dominating over the sunlight. If we look at magnetic fields of planets, we see these are the planets that have large magnetic fields. Here's the Earth's magnetic field. It's a dipole, just like a bar magnet inside the Earth, and you get this nice dipolar magnetic field with the south magnetic pole is actually at the north, and that's just one of the oddities of how we named it. The north pole of a magnet will point at the north pole of the Earth, which is actually a south magnetic pole. Jupiter, like we said, has a dipole, strong dipole magnetic field. So does Saturn, but they're actually much, much stronger. Here's a measure of the strength of the magnetic field at the equator of the planet, 31,000 nanotesla at Earth, but 428,000 at Jupiter, and 22,000 and 23,000 at the other outer planets. When you get out to Uranus and Neptune, you start to see they're kind of dipole magnetic fields, but they're offset. And the planets like Uranus are tilted over, and it's actually rolling in its orbit as opposed to up and down. Jupiter's pretty much straight up and down. Earth is tilted by 23.5 degrees. Mars, which isn't on here because it has only a residual magnetic field, and we'll talk about that in a minute, also at about 24 degrees tilt in its rotation. So we do see aurora in space weather on other planets. We've been to all the planets, Jupiter, Saturn, Uranus, and Neptune, and we've observed aurora at the bright poles of the planets. We've had missions like Galileo and Cassini and other missions, Voyager, going out to the outer planets and actually observing aurora on the planets. I see a question that says, do other planets' magnetic poles wander like Earth's does, and do they switch like Earth's? And the answer is probably yes. We haven't been watching the other magnetic fields of the other planets long enough. If you look at the wandering of the Earth's magnetic field, you see small changes over a person's lifetime. For instance, I live in Colorado, and I bought a bunch of maps to go hiking when I moved here, and they all had magnetic north as being, I think, about 10 degrees off of true north, and now that's about 12 degrees. I think I did that in the right direction, might be opposite. So in the 30 years I've been living in Colorado, the magnetic field of the Earth has shifted a little bit. But we have only been in the space age for a short while, and we just haven't been watching the other planets to know how much they move around. On Earth, we can tell that it's flipped many times because we see the signature in rocks. We can pick up rocks that have trapped magnetic fields in them and look at those rocks and say, hey, the Earth's magnetic field must have been the other direction 5 million, 10 million, 100 million years ago. We can't do that on other planets yet. We haven't landed and walked around and dug deep enough to look at other rocks and such. So here is a very complicated table I stole off the web just to demonstrate about the different chemistry or different compositions of other planets. Here we are at Earth with mostly nitrogen and oxygen and a few other things. Venus is mostly carbon dioxide, with nitrogen being a way second. However, Earth and Venus are about the same size. Venus is just closer to the sun than Earth. And Venus, the amount of nitrogen in the Venus atmosphere is similar to the amount in the Earth's atmosphere, meaning we think they both started with very similar atmospheres, but they just evolved differently. Earth was cool enough that we could have oceans that would pull carbon dioxide out of the air and put it into water. Venus was too hot and had what's known as a runaway greenhouse effect, that the carbon dioxide stayed in the atmosphere and there wasn't liquid water on the surface, and so the atmosphere just stayed hot and the carbon dioxide stayed in the outer atmosphere. We think the Earth probably had similar, maybe 60 times current atmospheric pressures at the beginning of carbon dioxide, but it all got absorbed into the ocean and then into rocks. The Mercury, of course, has here 10 to the minus 14 atmospheres, so 1 over 10 to the 14th amount of air as the Earth does. Mars is another carbon dioxide atmosphere, but it's only basically 0.5% of the Earth's atmosphere in density. So it has carbon dioxide, but there's not a lot of it. It's a very thin atmosphere. And that means that sunlight can reach much deeper into the atmosphere. The whole atmosphere is kind of like the upper atmosphere of the Earth at Mars, whereas Venus is so thick that very little light of any wavelength makes it all the way to the surface. It's all absorbed in the atmosphere, which is what makes it so hot. The temperature at the surface of Venus is about the same as a self-cleaning oven. When you put your oven in that scary self-cleaning mode and everything inside just bakes to powder, that's the temperature at the surface of Venus. So it's pretty hot. Then you go out into the outer solar system and you get these big giant planets that are mostly gaseous, and they're mostly hydrogen. You see Jupiter is 1,000 times pressure at the top of the atmosphere, what we call the surface, which is really the cloud deck. And it's almost all hydrogen, 90%. And Saturn is similar, 96%, and similar pressures at the top of the atmosphere. And you go out to other gas giants, Uranus and Neptune, and they're still also mostly hydrogen with some helium and methane. You're starting to get out into the outer solar system, and there's very little sunlight out there. This is a long ways away. And you get bigger and bigger molecules because temperatures are colder, and molecules can form, they don't break apart, and the sunlight isn't strong enough to break too many of them apart, except the very biggest things. And then you get way out to the dwarf planets and satellites of the other planets, and that have atmospheres, like Titan at Saturn has a nitrogen atmosphere and methane because it's cold. And we think that this planet probably hasn't evolved much because it's so cold. And it's very similar to what it was like at the very beginning, probably. And Pluto, we know, has a very, very tiny atmosphere, since we just flew by and measured it just this last year. So let's move on to MAVEN, and we'll talk a little bit about the point of MAVEN. You've probably all heard this many times before, but since I have an instrument on MAVEN, I'm going to talk about it. You can't stop me. Right now, Mars is a very hostile place. The mass of Mars is about 1/10 the mass of Earth, and its size is about half the size of the Earth. So it's a smaller body, gravity is less. It rotates very similar to the Earth, about 24.5 hours, and it has a tilt of its axis similar to the Earth, about 25 degrees compared to 23.5, which means it has seasons. It's in an odd elliptical orbit, which means when during part of the time, it takes about 2 years to go around the sun compared to 1 year for Earth. And at its closest, it's about 1.38 times the distance of Earth from the sun, but at its furthest away, it's about 1.67. So you get not only seasons due to the tilt of the planet, but you get those seasons exacerbated by the distance from the sun. So you're changing the amount of sunlight from, say, 30% up to 40%, depending on what part of the orbit you're in. The pressure, as I said, is just a fraction of that at Earth, and it's mostly carbon dioxide. And the temperatures at Mars are such that in addition to water freezing out at the polar caps here in the north and south, you get carbon dioxide. You get dry ice, basically dry ice falling out of the sky, the atmosphere freezing out, and enough of it freezes out on the seasonal poles for the pressure to change by from 6 to 10 millibars over the seasons. If you think about it, the Earth in the winter, the polar caps reach down to, say, Colorado. I grew up in Wisconsin. They definitely reach there. Snow covers the top of the planet, and that's exactly what's happening on Mars, except it's more carbon dioxide, some water, but also carbon dioxide. The temperature on the surface varies wildly. Sometimes around the equator in the summer, it can be up to 70 degrees Fahrenheit. But other times it's down to the temperature that carbon dioxide freezes out at. And it won't get much lower than that because you'd have to freeze out the entire atmosphere for that to get colder than that. I've already talked about the composition. Now, liquid water isn't stable on the current Mars surface. You can introduce water there. It can be there for short periods of time, but it immediately evaporates because the pressure is so low and the temperatures are not such that you can get a stable liquid on the surface. However, there's plenty of evidence that 3.5 to 2 billion years ago, so a long time ago, Mars actually did have liquid water. It had a much thicker atmosphere, maybe 10 to 30 times what the Earth's atmosphere is now, but all carbon dioxide. And that carbon dioxide would have formed a greenhouse effect, which heated the temperatures to warmer and and the pressures would have been high enough that you could have liquid water. There's plenty of geologic evidence. We look around, we see ancient seabeds, and we see water flow, and the rovers have gone and looked and see evidence of actually even current outflows of water at times when things have happened, volcanic activity and such. Some of the oldest flow channels over the surface are 3.5 to 3.9 billion years ago. Remember, the solar system formed 4.5 billion years ago, so it was a very young planet, only 1 billion years old. Some of the other flow features are less old than that, which indicates that a thicker atmosphere lasted for the first couple billion years of the life of the planet. And there's evidence in this artist's rendering based on geologic evidence that there was probably an ocean in the northern hemisphere. So what happened on Mars to make all of that water go away? And what happened to all the CO2 that was there and all the water? And we think that the process was atmospheric escape, and that's the whole point of the MAVEN mission, is to measure the escape of atmosphere at Mars right now, and then with our understanding and guessing in some cases of how solar activity and the planets and other things varied back 2-3 billion years, we can understand and extrapolate back to how much atmosphere escaped. And there are several processes for making an atmosphere go away. One is you can hide it. We talked about dissolving in oceans and sequestering in rocks, putting it in ice caps. Another process is thermal heating. The top of the atmosphere, if you heat an atom or a molecule hot enough, temperature really is just speed of motion of the molecule. And if it reaches escape velocity and it's going in the right direction, it'll just fly off the atmosphere and boil off into space. It's named after a guy named Jeans. It has nothing to do with pants. There's also hydrodynamic escape, where heavier things get pulled along, even though they're not heated up. Just the flow of lighter ones is enough that it drags along heavier things. And you get photochemical escape, which is heating through chemical reactions. So the sunlight comes in and it ionizes, and you get breaking apart of things, and the ions can be pulled off. And you can have heavier molecules hitting lighter ones and causing them to go faster and escape. You also have what we call sputtering or impact escape, where essentially the atmosphere is blown off by things hitting it, like dust from comets, dust in the solar wind, things like that. And finally, if we've ionized the top of the atmosphere with sunlight, and the solar wind comes along with all its magnetic fields, Mars doesn't have much of a magnetic field anymore. It has just frozen in patches of magnetic field. So it's like there'll be places where there's no magnetic field, and then there'll be a little lump of magnetic field, and then none. And we've mapped that all out, and it's very weak. So when the solar wind comes, it can penetrate very deep into the atmosphere and strip it away. It pulls off the charged particles. Remember that space weather diagram. This is the space weather diagram for Mars describing all the escape. Now we've designed the MAVEN mission to measure all these different things, the different outputs from the sun. My instrument measures the UV, other instruments measure solar wind things, and all the mechanisms going on the planet, escape, and all the different types of escape. And so we're mapping the inputs and outputs of the atmosphere of Mars right now and refining our models. And then just now, after a few years of studying that, we're starting to be able to extrapolate backwards in time. I see a question. What does it say?
The question is why did the liquid oceans that were on Mars back, a few billion years ago, why didn't they absorb more of the carbon dioxide as that happens on Earth?
So they did. Some did, but it's a slow process, and the oceans didn't last long enough for it to be a complete process. And the oceans were probably not as big. The Earth is covered with mostly water. 3/4 of the Earth's surface is covered in water, whereas we don't think that on Mars there was as much water covering the surface, so less would have been pulled out. And the escape mechanisms that I was talking about were happening fast enough that the carbon dioxide was escaping and breaking apart, and you get less and less greenhouse effect, so the temperatures go down and the pressures go down and the oceans start to go away. On Earth, it took billions of years for the CO2 to get absorbed into the planet's oceans. So you've probably seen this before. This is just describing MAVEN and the various instruments measuring the solar wind and the sunlight. Here's my baby, the EUV. It's about the size of a beer can. It's very small, sitting right on the top deck of the spacecraft. In fact, it's so small that they didn't put it on this drawing, something I'm not very happy about. They also have instruments that are measuring things in the solar wind and the magnetic fields and the atmosphere, the ionized part of the atmosphere and electric fields. And then instruments out on this platform looking down at the Earth's atmosphere, or the Mars atmosphere, measuring the temperature and composition. And the NGIMS is actually has an inlet, and when the orbit goes down deep enough, it sucks in some of the atmosphere and has a mass spectrometer and can tell you what the different atoms and molecules are. So to summarize, the sun is the primary source of energy, not just a primary, but is the source of energy for the solar system. And it's spewing out photons and particles and fields and creating space weather at Earth and other planets. How the different planets react depend on the peculiarities of those planets. What type of atmosphere does it have? How much atmosphere does it have? How far away from the sun is it? How strong of a magnetic field and what the orientation of that magnetic field are, things like that, all change how the atmosphere responds. And I repeated the same thing. Okay. I guess I saved the wrong version of this. But anyway, and the physics is all still the same. We can still use our knowledge of how it works. We just have to change the values of some of the parameters and run computer models and see how different the atmosphere reacts. And then we can make measurements with instruments on the ground and with satellites or probes to the other planets and confirm or find contrary evidence to those theories. And that's it.
A question about, do you have any theories as to why Venus has a thick carbon dioxide atmosphere and Mars has a thin one, since both planets don't have magnetic fields to protect their atmospheres from the solar wind?
That's a really good question. So Venus, one of the big differences between Venus and Mars is gravity. Venus is the size of the Earth, and it has very similar gravity as the Earth, whereas Mars has much less gravity. It's half the half the size and 1/10 the mass. So things are much easier to escape from the planet than they are at Mars. Things escape from the atmosphere of Mars much faster than they escape from the atmosphere of Venus. Another thought is that Venus was more volcanically active, and we do see evidence of current volcanic activity, and that means that it outgassed or had more of an atmosphere to begin with, so it hasn't all escaped. whereas Mars was less active, and so less atmosphere came out of the inside of the planet, and so there was less there to begin with, and was much easier to escape. Mars does have some volcanic activity, and there's evidence of it even in recent times. There are large volcanoes, but it doesn't have tectonic activity like the Earth does, where there are large plates and rift zones, and we think Venus does have that. Next question, oceans play an important role on the evolution of atmospheres. Is it possible Venus had less water? Do we still believe our oceans came from impacts from comets and asteroids? So that's two questions. Venus probably started with similar amount of water, but the water, it was hot enough that the water was a gas as opposed to liquid water on the surface. And water is actually a better greenhouse gas than carbon dioxide. So the more water you put in the air, the hotter the air gets. And that's part of the idea of runaway greenhouse on Venus, where the all of the water that formed with the planet is in the air and heating up the atmosphere and preventing it from forming liquid water on the surface. So Venus probably originally had about the same amount as Earth, but because it's closer to the sun, it lost it much faster. The ultraviolet light broke it apart, and we've actually been to Venus and orbited it and measured the upper atmosphere and have seen the hydrogen escaping from the atmosphere. Once you break apart water, you have hydrogen and oxygen, and hydrogen is really light and really easy to strip off. You lose a hydrogen, you lose water. Actually, you lose two hydrogens, you lose a water, but since it's H2O. Do we still believe our oceans came from impacts from comets and asteroids? I think that that's kind of a misconception, that it's not really later comets and asteroids, it's what the planets formed out of to begin with. There are all these objects, small planetesimals we call them. They're like comets and asteroids, but those are what collided and stuck together and formed the planets. And that was all happening at the beginning of the solar system and the formation of it. And that continued actually for the first billion years roughly of the solar system was still forming, and the planets were still accreting. There was still a lot of stuff. And there are periods like what they call the late heavy bombardment, which was really a continuation of the planets forming, not so much these random acts of comets and asteroids hitting the planets. Okay, I'm seeing lots of questions scroll by. Let me see, make sure I don't miss some. Is there a plan to send a rover or liner to explore the crustal magnetic areas in Mars' southern atmosphere? We have lots of plans to send lots of things to Mars. Whether governments get off their butts and spend the money to actually do it, I can't say. But yes, there are various plans to send rovers that will travel all over the planet and test different parts of the planet. There are even more far-fetched ideas of flying airplanes around on the planet and doing making measurements and things like that. Why is there so much nitric oxide in the upper atmosphere of Mars when it has so little nitrogen? So it has nitrogen. It's relatively less compared to the carbon dioxide, but if you count all of the carbon dioxide that the Earth had at the beginning and ratioed that with nitrogen, you would get about the same as the ratio of the nitrogen to the carbon dioxide on both Venus and Mars. So Earth has a mostly nitrogen atmosphere because all of the carbon dioxide went away, not because it has more nitrogen, relatively speaking. let's see, have we seen any CME direct hits on planets to see how they interact with magnetic fields and atmospheres? The answer to that is yes. We've witnessed a few hits on Mars since MAVEN went there. Unfortunately, we got to Mars during a very wimpy solar cycle, so there haven't been a lot of CMEs. But we have also seen on Jupiter and Saturn these orbiters, Galileo and Cassini, that have measured, and also the Hubble Space Telescope that have measured the aurora, have seen the aurora change with CMEs hitting the planet. So similar to what goes on at Earth. And is that the end of the questions? We can't hear you. There you go.
There was one question that was asked about Venus and plate tectonics, and whether you mean in the past there was water or currently, and what evidence we might have for plate tectonics in Venus. I think that's still very much up for debate, yes?
I'm not an expert, but yes, probably. If you look at the radar maps of the surface, you see what look like continents, and you see volcanic areas and such. So there's some evidence and guessing that it's going on. But the planet is kind of an odd beast because it's rotating very, very slowly, and it's rotating in the opposite direction. And the rotation of a planet has a lot to do with the motions inside the planet. So that's why it doesn't have a magnetic field, because it's the center of the planet isn't rotating fast. And when you rotate, things get put in motion, and that causes more activity of the plates, like on Earth, moving around and such. But that's about all I can say about it. I'm an atmospheric scientist, not a geologist.
We can try to get more details from somebody who's studied Venus and its tectonics, but I think that's the last question. I see lots of thanks from everyone about this. I really appreciate it, and I know everybody else does as well. Thank you so much for your time this evening.
Thank you. Everybody have a good night.
Thanks, Frank.